This is one of the hardest concepts, or the hardest, I don't say the hardest concept, but the hardest process of Calculus 1. The hardest process. Today we talk about the area problem. So for a lot of years, we've been able to find areas of geometric shapes, and we can find these areas. We realize that squares have equal sides, so S and S. So the area is just, well, it's like time width. It's S squared, the side squared. Well, think about a triangle. A triangle, the area of a triangle, well, triangle's half of a rectangle, right? So it is 1/2 whatever your base is times your height. And we use that idea to kind of divide, to find the area of this kind of stuff. If this was S, that was H, this is P, and this is still S, and this S. Well, we can kind of split these up into two shapes, right? We can say, well, that's the rectangle, that's a square. What would be the area of both of them? What would be the sum of the areas, right? So the area would be S times H plus, S squared, right? That's if we identify that. Well, what is this? We don't know what this is, right? Well, this is S minus H, or H minus S, right? This is that quantity. What's this times? S times H minus S. Basically a little bit of algebra. That's the area. Well, what's the area of a circle? Well, we know the components is the radius, right? And this is a famous one. So the area equals pi r squared. So that's another famous one. But these are all geometric shapes, right? These are all geometric shapes. But we have something this. What if we had to find this area? What would be the area formula? What would it be? What would it be? Well, people would approximate it and say, well, let's see a rectangle. Oh, these look like almost that they can fit like circles. That looks like a smaller circle. And these could be triangles. That could be a smaller triangle. That could be another triangle. This could be another triangle. And they would just, it's just an estimate. But I'm not 100% sure how to find the exact answer because it's curved. That's the only reason why you would say that. Well, that's a curvature that I don't know. It's not a circle. So, we are here kind of to solve this problem. And it has the hardest process to it. So this entire video is just going to be me getting you to the point of which we can find a formula for this. The entire video. This is the area problem. I have some curvy thing, right? Obviously, That looks like some function, right? And I want to choose my width. So I'll pick an interval from an A to a B, right? And I want to find the area of this thing. This says area under curve. Area under curve. Okay, how would you do it? Well, okay. How would you do it? Well, should we approximate it first? Let's do it. I mean, if we find an approximation, and we can make that approximation even better to the point we can make it exact, that could be a good thing, right? There's a lot of shapes that people could use during this situation. So if I say, well, if this is a curve, this is my interval, and I want to make this bigger because it's really important that you understand it. So if we have, ooh, that's not good. If we have, that's very bad. If we have a curve or function, ooh, it's zigzaggy, and we have an interval from A to B. We want to find the area. What would be the area of some function under the function? So what's the area equal to? That's what I'm saying. So for me, I could recognize this entire section as a rectangle. This entire section is a rectangle. And I can make this entire section a rectangle. And I can make this, and oh, but if I had a circle, it would just be too weird, right? Because we're going to have lots of circles, lots of weird shapes, and we're going to have a long formula of just, well, the function changes. We're going to have x squared, we're going to have other things, and our formulas are going to change for every function. So we want to be consistent with the shapes, and we want to use a consistent way of doing it. Because if we position our shapes other directions, we can't really do that for other functions. So we gotta be consistent. And right now you would think, well, what am I doing really? I'm taking, well, that's another right. Okay. We can approximate it by that approach, but now we have all this space missing, all this space missing. How would I? Well, we have an approximation, right? But it looks like we can't really make it better. So we're kind of stuck. We can't do it that way. So, what other way can we do it? Well, what we could do is we can say, well, that's a rectangle. And I'm going to cut this again. That would be another rectangle. And that's another rectangle. And that's another rectangle. And another rectangle. Another rectangle. Another rectangle. And another rectangle. And I'd say, well, that's a lot of rectangles. So isn't our formula going to be large? Well, we can multiply each side. We can just multiply. Wait. Yeah, isn't our formula going to be wrong? Well, think about this. That's all the space that we have to get back. So, would you say that the area of a curve is or under a curve is approximately equal to the area of the first rectangle, area of the second rectangle, area of the third rectangle, and so on. And before I go on, I'm going to write this right here. So, you said, we're going to say, the area of the approximately is the area of the first rectangle plus the area of the second rectangle plus the area of the third rectangle, all the way up to the area of our last rectangle. Let's call it N. Okay. How are we gonna get a more accurate result? Because we want to get an accurate result. Well, I'm gonna first mention how I'm actually setting up the rectangles right now. That might clear things up a bit. So, hey, how am I doing these rectangles? Well, I'm literally going to the function height and going down one. Going up to the function height and then making a rectangle like that. Going up to the function height, making a rectangle. So how can we make a more accurate... I know these aren't perfect rectangles, but how could we make a more accurate result? And these are going a little bit over the curve. But just by looking at what I'm doing right now, how can we make our area more accurate? This takes a little while to do. I know this isn't straight rectangles, but I'm trying to prove a point. How do we make it more accurate? We're still adding rectangles 1, 2, and 3 up to N, but what's happening? Well, there's a lot of rectangles, but how much are we off by? Just a tiny bit. We're off by a tiny bit. Except this might even balance out with that. We're really close. But we got even a greater approximation. Okay. Well, since this is the function height, we can just call the height of the rectangle f of x, right? Or, no. Every point is an x sub I. Because we're saying, well, this is the x position of the first rectangle, and the x position of the second rectangle, the x position of the third k. I'm going to say x sub k. The kth rectangle. So I'm counting my rectangle, saying, well, this is my x position of my second one, right? This is the first, this is the second. This is the third. I know this isn't the first, second, third, but I'm just listing them out. So do you agree with me? I'm just listing my rectangle's x position. Well, each rectangle, what I want to do is I want to make each rectangle an equal width. Delta x, the change x. And I'm going to set up a way of like finding out every width. Well, what's the width? It's delta x, right? So if our width is f of x, and our height of each triangle is just the function height of our x position of the kth rectangle. So if we put a k equals 1, the height of our first rectangle will be the function value of the x position of the first rectangle, right? So we can say that area is approximately equal to the height of the function at the first rectangle x position. And let me a little zoom in a little more. Let's zoom in one rectangle. So if we have a curve right now, I'm taking a little slice of a curve. And I'm saying, hey, where's my function height at? Sorry. Well, I'm always doing it at the left side, right? My function height, I'm reaching this point up to the function on the left side. The right side ain't reaching the function, right? So this is going to be the one I'm using, right? The x position of whatever rectangle k you're using. So, okay. Well, what's the height of the rectangle? It's f of x sub k, right? What is the width? Well, it's just delta x, right? So wouldn't you say that the area is approximately the sum of our rectangles? Areas of rectangles, right? We did establish that, right? So wouldn't you describe that more thoroughly and say the area is approximately equal to f of x sub 1 times delta x plus f of x sub 2 times delta x plus blah blah blah. How many rectangles do you want to even list? To the f of x sub kth rectangle times delta x. And what you can do here is you could factor all of your x's, right? And it would be f of x sub 1 plus f of x sub 2 plus f of x sub 3, all the heights of your rectangle, times, oh wait, sorry, up to the f of x sub kth rectangle, times your function height, or the width of the rectangle, and we would give that the area approximation. So that's the approximate area of your curve, right? I'm literally adding. So if you distribute it, it'll just equal base times height, base times height, base times height, base times height. But we want to factor it because we don't want to do that 100 times, right? So now we're just adding up the heights of your rectangle, as you see here. Where does the x sub 1 come from? Well, it's the x position of your first rectangle, the x position of your second rectangle, the x position of your third one. On the left side, the height of the function is f of that x position. That's the height of your rectangle, right? The base is always delta x. We're going to get all our rectangles equal width. Okay. So we got this far. What do we do here? Well, from this from this point, we have to introduce a different notation. Because we're adding a lot of rectangles. And I'm not going to want to write them all like this. So let's erase all this and keep that on our heads. Let's talk about summation notation. So, summation notation is a little sigma symbol, right? And means summation, right? And it looks like, the form looks like, okay, so let's figure out what that is. From 5 instead of n. So what in the world does this even mean? Well, summation means we're adding things. This is a sum. So it's the sum of all the things you're adding. Well, how do we even interpret this? This is what it's saying. We're finding the sum from k equals 1 to 5 of k. So, how we figure out the sum is we plug in 1 into k. Well, that's just 1. Right? And then we add. And then we go to 2. K equals 2. Well, that's just 2. We put a plus symbol. And then we go to k equals 3. We plug in that into k. Well, that's just 3, right? And then we go into k equals 4. What's that? That's just 4. And then we go to k equals 5. That's just 5. And we stop at 5 because it's telling us to stop at 5. So we're going to let k equals 1 through 5. Note that we're only plugging in integers. We're going 1, 2, 3, 4, 5. We're not plugging in decimals into k. Plugging 1 through 5 whole numbers. But how do we figure out this sum? Well, we just do it. In our heads, we say 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, and then we have 15. Okay, that's great. How in the world does this have to do with anything? Now, before I tell you the reason why we need this, what if we had a k squared? Well, you would do plug in 1 into k, right? 1 squared is 1. And then 2. 2 squared is 4. Plus 3. 3 squared is 9. And then we plug in 4, which is 16. And then we plug in 5, which is 25. And you would find your sum. Now, it turns out there's a shortcut to figuring these out. To figure out these summations. So, and there's also properties of summation. So I'm going to go for properties and summation formula. So, if we just had a constant a from k equals 1 to 5, your answer would be, we're going from 1 to n. Your answer would be n times a. If we're doing k equals 1 to n of a constant times k, we can pull out that constant and we can say, well, that's k then. K. Huh? If we have the summation of some function of k from k equals 1 to n. Now, so we don't have to have 1, but we sometimes do, plus some other function of k, or just k, we can separate these. So we can do this. You have to keep k equals 1 the same. So these are the properties, plus and minus. These are the properties of summations. Okay, so I'm going to go really fast because we only have 4 minutes left. 4 minutes left. Oof. So we have properties of summations. Well, let's go for summation formulas. Summation formulas. The sum from k equals 1 to any n of k equals n times n plus 1 over 2. Just literally, if you have this something and there's any number there, just plug in this into the formula. If you have k squared from k equals 1 to n, I think it is n times 2n plus 1 times n plus 1 over, I want to say 4, but it looks like it's 6, I think. See, I don't know what that's. Hold up. Okay, I'm correct. That is the form. The last one is if you have the summation from k equals 1 to n of k to the third power, that is n squared times n plus 1 squared over 4. So those are the summation formulas. Jot those down. Okay. I'm going to erase it real quick. We're going to do one example and then we're going to go. Wow. Oh, this is. I don't want to rush this. So if we have. Ooh, wait. What were we doing? We said the area is approximately equal to f of x sub 1 plus f of x sub 2 plus f of x sub 3 and plus dot 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 plus any f of x sub k. Ooh, what do we see there? Times delta x. Well, what does this look like? Looks like we're adding a bunch of things. Ooh, but they fit a certain pattern, don't they? They count from 1 to 2 to 3 to k. Wait, what? Times delta x? Wait a second. You want to set us up for something. That's right, that is the sum of the rectangles from k equals 1 to any nth rectangle. And I don't want to say k, I want to say n. That's right. That's an n. Or the kth rectangle up to the nth right. Sorry. So it says f of x sub k. We're going to count the rectangles. We're going to say plug in 1, we get the height, plus plug in 2, we'll get the second height, plus, and then we're going to multiply all of that by delta x. That's your approximation. And remember how we said we have to make the rectangle smaller? Right? We have to make the rectangle smaller. How many, what happens to the number of rectangles if we let the number of rectangles smaller? Well, we get is we're getting a lot of rectangles. But to be really exact, you are literally going to do this. Let the number of rectangles approach infinity. That's an exact answer. That's an exact answer. Because we're letting the rectangles approaching, the number of rectangles approaching infinity, that means our answer is going to be so precise, it's going to be exact. I'll see you in the next video, which will deal with how to do this kind of